Today I will basically give the tutorial talk about quantum random number generator. And basically, this is the summary of my talk. I would start with a more, let's say, didactical part, more introductory part on QRNG and the entropy estimation. And then I will try to give more detail into experimental activities in the different field of a random number generator, okay? And then go into the conclusion. So, first of all, what is a random number? Well, it is a number that is unpredictable, that we want to generate, and nobody should be able to predict the output. But how this line shows is, okay, this is defining exactly what a random number is not very easy, but we will come back to that. And of course, random number we know that are very useful, and in particular, they are crucial in all security applications, and in particular, crucial for QKD. Okay, so in any QKD protocol, you need a random number. Okay, so it's good that you have a good way to generate them. And of course, if we think to generate random number by, say, classical means like coin tossing, well, we get into trouble because we know that classical physics is deterministic. So basically, you can predict the output if you know the initial condition. Okay, so randomness is only related to ignorance on the initial condition. And the other way that we generate a random number is by pseudo-random number generator. But of course, these are, again, fully deterministic algorithms. Okay, so they are deterministic algorithms that generate sequences that resemble some random sequence. But of course, while they are very useful because they are simple, they're very fast, you can implement into simple hardware, they have for sure an intrinsic periodicity of the system. Okay? So indeed, as von Neumann was mentioning, if you want to generate randomness and you use deterministic algorithm, you are basically doing something wrong. And this is not just, let's say, an academic problem, because of course, if you look out on the past, people used a lot of such pseudo-random number generator, and this was a kind of simple version of it. The sequence of a random number is simply generated by this simple algorithm, okay? And if you start and you look at the numbers, well, they resemble some kind of random sequence, completely random sequence. If you plot 3 consecutive numbers, okay, you renormalize by the maximum 2 to the 31, you get something that resemble to be very random. But actually, if you look at a different perspective, these numbers are fully correlated. So basically, you have any triplet of number have a huge correlation. Okay, if you know 2 numbers, the third one is highly correlated. Okay, so this is completely not random at all. Okay, again, this was a very old model, but we know that even today, even with very sophisticated random number, like this was a random number generator based on elliptic curve, so a very complex mathematics, but this kind of random number could have a backdoor, because if you know exactly how this is generated, it is possible to predict the output. And indeed, this was a commercial product, okay, that was actually discouraged from the market, okay? So people use it. It's 10 years ago, so not very long ago. A very commercial random number generator was abandoned, okay, for this reason, okay? So what is the alternative? Well, we are here in the quantum cryptography conference, so we want to go quantum. And why quantum random number? Well, because, of course, quantum mechanics offer the guarantee that measurements are intrinsically random, okay? So the output of a measurement, in general, cannot be predicted in advance, okay? And the very important stuff is that even if you have all the knowledge of the initial condition and all the measurement stuff, well, you are not able to, in some cases, to predict the output. And so the randomness is not related to ignorance, but is related to quantum physics, okay? So this is the crucial difference, okay? But, okay, what do we really mean by a random number generator, quantum random number generator? Well, in the most basic example, most simple case, if you have a D-level system, you have a quantum state, you know it, is a pure state, and then you have a projective measurement, okay? So let's consider a D-level projective operator. Well, you know that you have the Born rule predict what is the probability of getting the output, okay? And nobody, if we trust quantum mechanics, nobody can predict what is the output of each single measurement, okay? We can only predict the probability distribution, okay? But great, so this is a quantum random generator, but how we can measure what is the amount of randomness that this device contains? Well, there are in this case, very simple parameters. One is the so-called classical mean entropy that is very relevant for the single shot case. Single shot case means that you run the experiment one time and you want to predict the exact single outcome, okay? For the single outcome prediction, what is relevant is basically the maximum of the logarithm of the probability. So basically, the maximum outcome is related to what is called the guessing probability. If you want to guess, if you want to put your money on the output, you would bet on the most probable outcome. But of course, if you go to asymptotic case, so in an IED case, the relevant parameter becomes the Shannon entropy, okay? The Shannon entropy defined in this way, and this is basically related to the probability of an n outcome string, okay? And the guessing probability is given by this expression here. You can notice the n times here, okay? So this is very basic, very simple random number generator. Okay, but then what we have to do? Well, actually, estimating randomness is not enough. You need to do what is called, you need to do an extractor, okay? So what you need to do, you need to post-process your data and start with a raw string with the, let's say, not complete randomness, estimate what is the entropy of your system, and then with an extractor, obtain a uniform distribution. Because at the end, we need typically uniform distribution of outcome, okay? And this is related to the entropy of our source. And what about extractors? Well, there are several ways of doing extractor. One is the so-called deterministic extractor, okay? So they start from fixed input length and fixed output length. And these are good extractor, but they work only for particular input distribution. So they do not work for every possible input distribution. And there are also what is called deterministic but variable length extractor. So the idea is that the input is a fixed length, but the output could change its length. And a very simple example is the famous von Neumann extractor, okay? So the idea, what is this idea here? Well, let's suppose you have a very biased sequence of 0 and 1, okay? So 0 appearing much often than 1. Well, basically von Neumann's proposal, well, if you consider just pair of numbers, you can discard the 0, 0, 1, 1 pair, and you can associate a 0, 1 to the 0, 1 and 1, 0 pair, okay? Even if you have a bias, the 0, 1 and 1, 0 probability are equal, so you get at the end an unbiased sequence, okay? This von Neumann method is not very efficient, but it was generalized by Perez in '92 to get basically a sequence that is close with the length that is close to the Shannon entropy. Okay, so this is very efficient to Shannon entropy. Of course, these require input that are not correlated. Okay, this is a fundamental assumption here. In general, what we really need is what is called seeded extractor, okay, that works for most general cases, okay? For seeded extractor, it means that you need n bit of weak randomness and v bit of uniform randomness that you put together, and then you use this to extract, okay, n bit of almost uniform. And the idea is that, depending on the extractor, you may have an extractor like the so-called Trevisan extractor, in which the seed, this is called, this term here is called seed, is a polylogarithmic with respect to the n, okay? So you need few bits of seeds, or you can use what is called the Toplic hashing, in which the seed is very long, but you can recycle, okay? So again, you don't need to change seed every time, okay? So this is the way to do the proper random number generator. And finally, let me also mention the very important aspect here, is that actually what we will see in the next part of the talk is not only random generation, but also two important protocols, and in particular the randomness expansion. So the idea is that randomness expansion that exploits basically entanglement, well, you start with a small random seed, okay? And then you want to produce a much larger random sequence based on the laws of quantum physics. The other protocol called randomness amplification instead, you start from a seed that is what is called a weak source, so it's partially correlated and partially biased, and then you want to amplify this and to get a real uniform output, okay? Very good. So let's go to the final part, randomness testing here. So what is very important to mention is that actually when you have a sequence of random number, okay, there is no way to check if a finite sequence is really coming from a true random number generator, okay? So every sequence could be generated from a true random number generator, okay? What we use typically are only statistical tests that detect suspicious sequencing. So what you can detect is that if a sequence is not generated by a true random number generator, then there are ways to check it. Okay, so it's only a counter examples, so to say. Okay, and there are many suites that are designed to check if you have suspicious pattern, for instance, and then from this pattern you can infer that your generator is not working well. But very important note here, statistically, even a very perfect random number generator would fail such tests time to time, because it's totally statistical. Because as this, you see here, right? Statistically, even a perfect random number generator, you can produce, let's say, a sequence of 0, 0, 0, 0, very long sequence of 0. Okay, this is very unlucky, but somehow possible. Okay, very good. But now, can we go to more deep, let's say, estimation of entropy? Well, the model that I described before is a very simple and very simplified way of estimating the true randomness of a quantum random number generator. We need, of course, more advanced tools, okay? And such advanced tools are related to what is called conditional entropies, okay? And in particular, what is very important is the so-called conditional mean entropy, okay? That has this definition that from this is very, well, it's not very intuitive, its meaning, but we will see soon why an intuitive and operational interpretation of this quantity that basically is related to the joint state between the system A that you want to, from which you want to generate randomness, and the system E that is, let's say, the eavesdropper, okay? And you have this expression that tells you what is this conditional mean entropy. Of course, another important entropy is the conditional von Neumann entropy that again is related to the joint state with the standard von Neumann entropy. Very importantly, the mean entropy is called mean entropy because basically is the lowest entropy that you can define with suitable properties. So the von Neumann entropy is always bigger than the mean entropy. Good. What are the meaning of such quantities? No? So such conditional entropy. In particular, what we are considering here is this situation. So we have this state A, rho A. We want to generate randomness from this quantum system, okay? But such system is correlated with the environment, Okay, so actually the system is more general. It's described by the joint state. Okay. Of course, after measuring the system, now the system A, let's say, collapses into a classical system. So now you have what is called a classical quantum state. Okay, so the system A now become a classical system. I call it Z. And now you have correlation between classical information on Alice side and quantum information on eavesdropper side. Okay, and now if you compute the quantity, the conditional mean entropy that was defined before, actually this give you a much more, let's say, simple expression, and with also a very important interpretation. If you calculate this 2 to the minus h quantity, you get this expression here. And this expression is exactly the guessing probability of an eavesdropper, because basically is if you consider this term here, this is a measurement on the eavesdropper side. Okay, so basically this is the probability that this dropper correctly guess the Z value. And then you average overall possible output. Okay, so basically this really means that this quantity has a very important interpretation. Is related to the guessing probability of the Z output from the information that eavesdropper has with this quantum state sigma Z. Okay, so this is why this mean entropy is so important. But actually, we need a little bit refinement, because for finite size scenario, it's very important to define what is called the smooth mean entropy, that basically requires some, let's say, some maximization around some state around your original state rho. So you take rho, you consider a small ball around rho, and you want to maximize the mean entropy around this ball, and you call this quantity the smooth mean entropy related by this parameter epsilon, that is basically the size of such ball around your original state, okay? And we have a very important theorem called the quantum leftover hash lemma that tells us that such quantity, the smooth mean entropy, estimated the amount of random bits that are secure against quantum side information. Going into more technical detail here, the theorem says that whenever you have a string of n bits and you have a given extractor that was called f is what is called a 2 universal hash function, okay? If you choose the output length of such extractor by this expression here, okay, this output is what is called 2 epsilon close to a uniform and independent string, okay? So basically, to summarize, the smooth mean entropy with a little correction tell us what is the output length of my extractor, okay? If I can evaluate the smooth mean entropy, I can know exactly what are the length of my final string, okay? So this lemma is very crucial to give the final length of the random string that we need, okay? So the problem is to estimate now the smooth mean entropy. There are several techniques. Of course, in many cases, you can use the IED condition. So basically, if you have a sequence of n run, and basically in each of these, you repeat the same measurements, and you can consider that the total system is a joint product, a tensor product of a single system. Well, basically, you have these asymptotic equipartition properties that tell us that basically the smooth mean entropy of this tensor product system is lower bounded by basically the sum of the von Neumann entropies minus some correction that scale is like the square root of n, okay? And this scaling tells us that in the infinite limit, you go back to the Shannon theorem, basically, okay? So when you go to the very infinite sequence, basically the smooth mean entropy approximates the conditional von Neumann entropy. But also you can use the same quantity here, that the smooth mean entropy of the total system is basically lower bounded by the n times the mean entropy of a single system. Okay? So basically computing the mean entropy or the von Neumann entropy of a single system tell you about the final mean entropy of your system. But in other cases, many other cases, what happens if you cannot assume ID? Well, in this case, you need to consider entropy accumulation theorem, okay, that was already introduced in a previous talk. And here I just summarize what this theorem is. Actually, I'm using the general entropy accumulation theorem that is presented in this paper here. And the idea is that whenever you have, let's say, information that is generated on system A, okay, that are correlated with some environment E, okay, these Z are classical information. The only constraint is the so-called no-signal condition to apply the entropy accumulation theorem. So the idea is that such system, each of these systems, do not reveal information about the past output, okay, but only on the output of the same on the same time, let's say. So the idea is that you have some map called MJ here that you perform some operation and you get some classical data out of it, okay, and then part of such information is actually leaked to the eavesdropper, okay, to the environmental system. The important assumption, as I said, is that in each of these operations, basically the information that is leaked here only goes to E2, okay, is fully contained in E2, okay. And under such assumption, basically you have something that resembles the equipartition theorem, because basically the smooth mean entropy, the total smooth mean entropy, is basically a sum of the von Neumann entropies of the single, let's say, on the single copy somehow. This is a complicated expression here, but the important feature is that basically you can decompose the total entropy into entropy of single shots somehow, plus some square root of n corrections, basically. Okay? So these are the most important tools that are used in a random number generator. And now let's say I described what are the typical the trade-off in security that are used in quantum random number generator, and I will discuss several realizations. Okay, so basically now you can go from what is called trusted random number generator that was described before. So basically our system in which you have full information about your input state, full information about your measurements, so they are fully trusted, you know everything, and of course, and they can achieve very high speed, okay? Or you can go to what is called the fully device-independent QRNGs, in which basically you exploit entanglement to determine the randomness, so you increase the security of your system, but of course, you reduce the speed and the simplicity of your device. And then there are the so-called semi-device independent QRNGs, which basically you have a trade-off sometimes. So basically you get some partial assumption or some partial characterization on your device, but not full characterization, but still you have the possibility, the capability of determining what is the correct randomness, okay? So basically now I will review some of the, of course this is not, let's say, will not be exhaustive, so is a selection of some example for the different parts. So if I forgot some of them, it's not on purpose, let's say, okay, just for matter of time. So let's start from the simple. So let's start from the trusted QRNG. So as I said, just to recap, is everything is known. You know the state, you know the measurement, and you need to consider classical mean entropy and classical Shannon entropy. Okay, great. First simple and famous example, well, the beam splitter random number generator. You get a photon, you go to a beam splitter, and you randomly, and the photon randomly is detected on one or the other detector. Okay, this is the simplest example of a random number generator, and actually this is the physical point, starting point of this commercial, of the Quantis, ID Quantic commercial random number generator that was one of the first random number on the market. But of course, you can exploit single photon in several times. For instance, you can exploit the arrival time of a single photon. If you have a stream of light, okay, at the single photon level, then the detection time is completely unpredictable. And then you can exploit the fact that you have Poissonian statistics, and you can consider, for instance, the different time of arrival, and depending of if the time of arrival is larger or bigger of the interval, you can associate a 0, 1. So it's another way to create an unbiased sequence of 0 and 1. Or even, again, considering light and a single photon detector, and then considering some sampling time that is very slow. So you, in every sample time, you count how many detection you have. And depending if you have an even or odd number of detection, well, you call it a 0 or a 1. Okay, so these are a simple example. And let me also mention this example that in our group we proposed a few years ago. So the idea was to exploit a similar principle, but with a CMOS pixel array. But the idea is that now, if you have a very fast clock that sample the detection, the arrival detection of a stream of photon into a single photon detector, well, basically you have a very, very, very biased sequence, right? You get a 1 only when you get a detection, and you get a 0 otherwise. And typically this is highly biased because you have more 0 than 1. But in this case, assuming that you have indeed independence of such detection, you can apply the von Neumann-Perez algorithm to remove the bias, and then you can achieve up to, let's say, 5 megabit per second for every pixel of this single photon detector. Okay, so this is somehow this scheme is a kind of generalization of every possible time of arrival scheme, because basically this is really considering the most fundamental information that you can get. You are getting exactly the information of the arrival of each photon condition on the clock repetition rate. Good, but of course, can we go faster? Can we go faster than megabit per second? Well, if you want to go faster, you should or increase here the pixel size, or you have to go to continuous variable protocol, because we know that continuous variable, you can use, let's say, photodiode that are much, much faster. And in this is what the very famous result on 15 years ago, using basically vacuum fluctuations, so measuring the vacuum with an homodyne detection to get, let's say, random number, in this case at 6 megabit per second, but was showing that also with continuous variable you can generate. And here, on the physical point of view, what you are doing here, you are basically measuring somehow the electrical field of the vacuum, and we know that the electrical field is 0 on average, but you have indeed the quantum fluctuation of the electric field that give this Gaussian distribution, from which you can extract the numbers. Of course, this is a 15 years result, but we have tremendous improvement in the last year, and I cite here a few relevant to me results. This paper 2 years ago, this was a similar approach, vacuum and homodyne detection, but with an integrated chip, and they achieve 100 gigabit per second random number generator. So going from 6 mega to 100 giga is huge improvement. And real time, I think that is coming soon also on this kind of setup. Also, I pointed out this paper in which they use, this is, to my knowledge, one of the fastest real-time quantum random number generator. So 20, let's say 19 gigabit per second, real time. What means real time? Well, it means that all the extraction process is done in real time. Okay, so all the analysis and the extraction is in real time. So you have a real time stream of 18 gigabit per second random number. Also in this case, there was some photonic integration, and finally also very recent paper here on the archive in which is again integrated, but while before the integration is only done on the homodyne part. In this paper here, they show basically full integration from laser to electronics to everything. So all integrated in the same chip for achieving, again, in this case, post-processing 6 gigabit per second. Okay, so you see a lot of improvement in this 15 here for a very, very fast random number generator. Of course, if you want to run a very high-speed QKD protocol, you need such random number generator, such speed. If you want to run a QKD protocol at 1 gigabit, okay, 1 gigahertz repetition rate, you need such a number, okay? Because you need many bits of randomness for every quantum state in a QKD protocol. And also let me mention a very relevant example that is the random phase of gain switching laser. So basically when you have a gain switching, you are basically amplifying the vacuum. Gain switch means, let's say, very roughly speaking, turning on the current of a laser very fast, okay? So basically what you're doing, you are somehow amplifying the vacuum and create a coherent state. But the phase of the coherent state is completely random, okay? So every time you turn on and off the laser, basically you create a pulse with a random phase, okay? And the idea was exploited in this paper, okay? In two papers, two examples. There are several realizations in which basically the idea here is that you create a sequence of pulses and then you have a delay and you make an interfere the two pulses on a beam splitter. And since the two pulses has a random phase, you have a random interference at the output, and then you create a random number. Similar here, they use, let's say, the steady state and not just the pulses, but the principle is very similar. And this is particularly relevant because basically this physical principle is at the basis of another important commercial QRNG, another that is the QRNG based on the Q side, and they have 1 gigabit per second performances. And the idea is that, again, now they are using two lasers, okay, that are interfering on a beam splitter. And then, again, since these two lasers is a completely random phase, they give a random interference effect. And by reading the outcome, you can generate random numbers. Good. So this is for the trusted part. But then let's go to the more advanced, like the semi-device independent part. So what is semi-device independence? As I said, you have some assumption, some condition on your device. And let me start by the so-called source device independent, QRNG. And what is exactly? So the idea is that let's consider the simple photon, okay, and beam splitter case. So how you can distinguish that your randomness came really from, let's say, a pure state and not from a mixed state? If you just look at the outcome, well, they have exactly the same statistics, okay? But this is the true quantum randomness. This is, let's say, the classical randomness. And actually, the mean entropy should be able to distinguish these two cases, okay? And so how we can distinguish? Well, the idea is that even if you have a complete untrusted source, so this is why this is called source device independent. So you have an untrusted source, but you have a full trusted measurement device, okay? So again, so this is semi-device independent because one part is trusted, the other part is not trusted, okay? And in this case, what you can do, well, there was an old proposal in 2007, which basically, for single qubit, what you can do, if you sometimes perform a tomography of your state, okay? You can evaluate the conditional mean entropy on the Z measurement. So you use the sigma Z measurement to generate randomness, and basically you use the other information of the other two bases, the X and Y bases, to determine the randomness of the Z basis. Okay, so you use the tomography to give information on your state. But what happens if you have larger system? Well, we proposed a few years ago a way to certify the mean entropy using the uncertainty principle. Okay, so the idea is the following: because when you have two observable, okay, you have some uncertainty principle that works not only in the standard variance form but also on the entropies, and in particular, let me mention this result in which basically the mean entropy of one measurement is related to another entropy that is called the max entropy in the other basis. Okay, and actually, if you this requires tripartite state, but in our case we only have a bipartite situation, so we can neglect the B space, and so you have a simple relation between the conditional mean entropy on one basis with the max entropy. Now this is a classical max entropy on the other basis, and the idea is that now what you can do with even a very large dimension system, what you can do, you can use one basis to generate randomness, and basically the other basis to estimate the amount of randomness that is generated with Z. Okay, by exploiting this relation, you basically have a direct access to the guessing probability. Okay, so again, this is very similar to what is done in QKD, right? In QKD, in standard BB84 or efficient BB84, you typically have one basis for key generation and one basis for eavesdropper detection. Okay, so this is exactly the same principle. Okay, so the Z basis is random generation, the X basis is for eavesdropper detection. Okay, and we tested with the single photon and tangled photon on one qubit and one Q-quart, and we see that you can achieve quite nice results. But of course, again, to go faster, you need to go to continuous variable. So you can extend and generalize these to continuous variable systems, okay? And again, now measuring not a single quadrature, but two orthogonal quadrature, okay? And again, you have an uncertainty principle that allow to bound the randomness on one basis by using the result on the other basis. And as you see from this graph here, no, in the blue are where the number are generated. In the red part, we switch the basis, and so we check the presence of an eventual eavesdropper. Okay, and so with this, you can achieve in post-processing more than 1 gigabit per second, 1.7 gigabit per second. So the idea is that what is to me is relevant is that introducing this kind of let's say source device independent, semi-device independence, so you increase the security because you are, let's say, lowering the assumption of your system, so you are completely untrusting the source, but you maintain quite high generation rate. So performance are not reduced. Okay, and this could be also generalized by using a more general measurement using P of M. And why this is important? Because in continuous variable we have a natural P of M that is the heterodyne measurement. Okay, the heterodyne measurement basically is, let's say, is modeled as a projector on coherent state. Okay, is 1 over pi the projector of a coherent state. Here there are some technical details about the discretization, physical discretization, so you need to use this discretization to perfectly describe your system. But the idea is that when you have a P of M, there is a very simple rule for estimating the mean entropy. Okay, basically what you do, well, you calculate what is the maximum probability of outcome. Okay, for P of M, such probability of outcome is less than 1. Okay, so this gives you the randomness, already the randomness. Okay, the fact that nobody can, whatever input state, you can never have 100% probability of outcome. Okay, and so for instance, for standard POVM, you have 1 over pi, that is the maximum probability of outcome, okay? And with this result, actually, this is the basic of one of the commercial product of Thin Quantum that I was said before. I'm one of the co-founder, and indeed, you see that in this source device independent framework, you can achieve now in 300 megabit per second. Now this is a real-time streaming output. Okay, so the internal source is 2 giga, but the final secure bit streaming is 330 megabit per second. Okay, so we have a commercial product with also increased security of such a kind. And very recently, we had 2 papers in which we implemented this kind of generator in photonic integrated circuits with achieving 20 gigabit per second in post-processing, but also using femtosecond laser written glass chip that are very interesting because basically you can have a very, very low loss. Okay, they are very low loss devices, so you can really go to have a high signal to noise and to achieve a very, in this case, 42 gigabit per second post-processing. Good, but okay, let me skip this, go to the more measurement device independence, because there are, okay, not only source, but can we also have QRNG with the measurement device independence? So basically now you trust the source, but you don't trust the measurement. Can we do quantum random? Yes, the idea is let's say, is the complementary of the source device independent. The idea is that now what you do, you prepare a set of trusted state, okay? And you only use one to generate randomness, okay? And the other state that you send are used to test your system. So you test your untrusted measurement with your test state here, okay? And similarly, I don't go to the detail, but similarly on the Fiorentino paper here, well, you have a way that given the untrusted POVM, you characterize the untrusted POVM with your input state, and then you can bound the guessing probability when you inject what is called the generation state. Okay? So it is, as I said, is a complementary of the previous technique, and recently, there are 2 nice implementation of this with basically with continuous variable, again to increase the generation rate. Okay, and here, again the expansion rate now is 5 kilobit per second. Okay, with also entropy accumulation security. Okay, and the idea is that now you can do similar. You are not sending, let's say, qubit, but you are sending coherent state or 4 or 16 different state, and depending on the output, you generate randomness. What is important? Why this is expansion? Actually, this is an expansion because you need randomness to choose between the input state. Okay. Even for the source device independent case, you need, let's say, randomness to choose between different measurements. Okay, so the idea is that you have some initial seed of randomness, and with this you can expand to more longer sequences. Okay, and also there is the so-called self-testing that are between the source and the measurement device independence, and one example is this, for instance. So the idea is the following. You have preparation and measurement that are untrusted, okay, but uncharacterized. But in this case, you have only a single assumption that basically your preparation stage is preparing a 2-dimensional system. Okay, this is the only assumption. You don't know nothing about it, but you only know that this is a qubit. And then you can show that if you evaluate some function of the measured probabilities, so these are the conditional probabilities, you can guess the output, the guessing probability. Okay? So now again, we don't know if there are single photon, continuous, discrete variable, whatever, you don't know nothing. sorry, in this case, you only know that it is a two-dimensional system, okay? But nothing more. And similarly, you can achieve what is called unambiguous state discrimination. So basically, now the assumption is that well, you don't know if it is a qubit or not. You only know that the input state are not orthogonal. Okay, the only assumption is this one. So you have input state, in this case, just two that are not orthogonal. Okay, if only by this simple assumption you can show that by using a semi-definite program, by, again, exploiting the experimental data. So you have the data, okay? And using the data, you can show that there is a way to describe the quantum randomness, okay? What is the physical principle here? The physical principle is that since you have two non-orthogonal states, there is no system that is able to discriminate, okay? So whatever measurement is contained here, this measurement should have some quantum properties, okay? Otherwise, why this overlap is important. And also this overlap actually can be replaced by a so-called more physical assumption that is an energy bound. So basically is a bound on the energy or the average or the max energy emitted from the state. And of course, when this bound is very low, it reduces to an overlap bound, because if you have an energy, let's suppose that you have an energy less than one photon, let's say, the energy of a single photon, well, it means that the state should have the vacuum component, okay? So the vacuum component is always there, and so basically you have that the overlap cannot be zero, cannot be orthogonal, okay? And also there are some results in which these kind of random number generator are implemented with the heterodyne receiver, with the two outcome, or with two input, or with many outcome. Okay, so you can again, once you have the framework, you can use whatever physical system you prefer, and also this recent work by the Vigo group that again, you are basically generating a vacuum or a very weak coherent state. Okay, and since these two states, let's say, are not orthogonal, the principle is similar. You can generate randomness in a semi-device or self-testing manner. Okay, great. So let me go to the final part, that is the device independence. So what is time left? Is 15 minutes, more or less? Oh, just to know. Okay, great. So, device independent now. Well, I think that we know about Bell inequality, that we know that this is basically related to fundamental problems, no? Of quantum mechanics. We heard a very interesting talk yesterday and about discussing about locality and reality of quantum mechanics. And we know that this Bell locality and the Rocker realism in this form was violated in many different experiments, and also in a loophole-free manner. Okay, but the important point now is that we can use the Bell inequality to certify the entanglement. Okay, so the fundamental idea is that whenever you violate a Bell inequality, okay, you are sure that there is entanglement in your system. Okay, no matter what you are using, but you have entanglement in any case. Okay, so this is the standard CH-SH scenario in which you have two input and two output, and when you consider the conditional probability, if they violate a Bell inequality, you can prove, basically you can prove entanglement. And in this very seminal paper in 2010, basically they showed that when you calculate the Bell parameter S, this is how it's defined. This is the sum of the 4 correlation terms, and each correlation is defined in this way. Well, you have a direct way to calculate the guessing probability of a single outcome. Okay, so you are considering randomness here only on a single outcome. Actually, you can consider the randomness of the two outcomes. It's a little bit complicated as expression. So I reported this because it's a very simple expression. Okay, you have a direct connection between Bell parameter and the guessing probability, and you can easily check that if the Bell parameter you don't violate the inequality. So if the Bell parameter is 2, the guessing probability goes to 1. Okay, so you can, the eavesdropper have full information. Okay, but whenever you violate the inequality, this guessing probability is less than 1, so you get some randomness. Of course, you require the loophole-free violation. And in this first seminal paper, they use atomic system. And again, this is a randomness expansion because in a Bell inequality, you need random input, X and Y, to run the system. So this is also an expansion protocol. In this paper, actually, they get one entanglement event every 8 minutes. Okay, and over a long experiment, they achieve 42 random bits. Okay, this was the first achievement. So his result was, but now we had much better and much improved result. And these are the two parallel important work in 2021 in this Nature Physics. Basically, they are back-to-back publication here, in which basically they showed with the very remarkable and very important system with very high overall detection efficiency, because using photon, the detection efficiency is the most critical loophole. So achieving very high overall detection efficiency, they go to the, let's say, 10 bit per second expansion, okay? Using, in this case, one paper using even the entropy accumulation, a generalized version of the entropy accumulation, so it's very strong from all the security point of view. So now you go to bit per second. So it's very complex, very complicated, but as I said, this is the overlasting security. So the best security that you want, but of course the performances are a little bit lower, but is a very remarkable result that we can indeed achieve, full device-independent quantum random number generator by photonic system. Okay, and let me conclude by briefly mentioning some interesting, let's say, perspective in which we are interested in the last few years. And basically, is the idea is to have a device-independent QRNG, but using what is called sequential measurement. Okay, so what is the idea of the sequential measurement? So the idea is that now you don't have only Alice and Bob system, okay, but you have a sequence of Bob. Let's say Bob 1 is doing some measurement and some outcome, but then the quantum state is not blocked. No, it's passed to another observer. It is called Bob 2, and then you go to Bob 3, and so on and so forth. Okay, so the idea is that you can repeat the measurement over the single system, and somehow it's a kind of intermediate scenario between full communication and no signaling. Okay, because there is signaling, but only on the Bob side. Okay, because of course the Bob 2 has signaled from Bob 1. Okay, and what was shown in this paper in 2017, this is, to me is very remarkable, is that even if you have a single E-bit, so you have a 2 qubit, 2 entangled qubit, okay, you can, of course, you have these kind of conditional probabilities, okay, you have all the inputs and all the outputs, but what they showed is that you can achieve an unbounded number of random bits, okay, by continuously repeating the measurements. Okay, this is very remarkable. You have a single bit and a single entangled pair, but then you measure it again and again and again, and then you can go to infinity. And every time you have randomness. You extract 1 bit of randomness every time. okay? Very good. Well, of course, what do you need? Well, you need what is called weak measurement, okay? Because of course, if you use projective measurement, you're destroying entanglement, so everything does not work. With weak measurement, basically you have to couple the system with an ancilla and then measuring the ancilla, and depending on the interaction strength, basically it depends how much you are interacting with the system, and there is a very nice information disturbance trade-off that tell us that the most you interact, so the most you get information from the system, okay, the most you disturb it. And the less interact, you less disturb it. So it's a very important principle in quantum mechanics. Of course, this is from the implementation point of view, this is complex because it requires some kind of non-demolition measurement, but there are proof of principle experiments that can be done even without the quantum demolition measurement. And in particular, you can, for instance, what we did with the photon is to couple 2 different degrees of freedom, okay? If you couple 1 degree of freedom of a photon with another degrees of freedom, okay, and you measure the second degrees of freedom, you are basically doing a kind of weak measurement on the first. You have a polarization, you couple with the path, you measure the path, and then you have a weak measurement on the polarization. This is the way proof of concept experiment has been realized. Unfortunately, for what we noticed is that this original protocol, okay, we tested in the lab with this technique of, as I said, of using coupling between different degrees of freedom. We tested with a photonic system, an entangled system, and what we realized that the original protocol is very interesting because you have an infinite number of bits. However, it's very, let's say, low tolerant against imperfections. Okay, if you consider very simple model like let's say white noise model. Okay, well basically only if this white noise is less than 1/1000, basically you can extract more than 1 bit with respect to the, let's say, the standard device independent scenario. Okay, so you need to have a very small amount of noise to gain with respect to the standard device independent scenario. And so we came up to a different protocol that actually is quite simple from the point of view, but you can improve with the previous one. And the idea is that in this case is very simple. So you have from Alice and Bob 1, you have almost the standard CHSH parameter. So the state is a maximally entangled state. You have almost the CHSH measurement because here you have a weak measurement on the sigma z, okay? And the idea is that whenever you measure the sigma on Bob 1, whenever you measure a strong measurement, then you stop because you know that say the system now is no more entangled, so there is no need to go after. But when you measure with a weak measurement here, well, you measure the Bob 2 with the other, again, sigma z and sigma x operators, okay? And the idea is that basically, this is a very rough, let's say, rough explanation, but when you are measuring the weak sigma z, the other sigma z in Bob 2 is not altered, okay? So basically, when you measure a weak sigma z, you can basically violate a Bell inequality between the operator sigma z of Bob 2 and the sigma x of Bob 1, okay? So you can have a combined Bell inequality between Bob 1 and Alice and Bob 2 and Alice. And this technique allows to demonstrate a kind of the randomness. And here you can see that in this case you can achieve, for perfect case, you can achieve 2 bits of randomness. And what is remarkable that is independent on the strength of the weak measurements. Okay, so only for 0 or maximal strength, of course, you get 1 bit because you go back to the previous case. But for all other strength, you get 2 bits of randomness. But of course, what is also important is that this is much more robust with respect to imperfection. And here we show the experimental data, in which we basically overcome the limits of the standard CHSH protocol, or even the previous presented protocol. Okay, and then the blue curve is the result in our case, and clearly you can achieve more than 1 bit for much higher, let's say, a level of noise. Okay, and of course I cannot go to the details, but if you go to this paper here, we also studied all the, let's say, the geometry of the sequential quantum correlation, because basically what happened with this sequential measure is that you open up a Pandora vase of quantum correlation, because now you have quantum correlation with constraint, so the geometry is much more complicated and complex, but actually the idea is that such kind of correlation are at the boundary of the set of correlations, and so since you are at the boundary, you are in a kind of, let's say, device-independent scenario, okay? So with this, I'm basically going to the conclusion, and in summary, what I let's say, try to explain in this tutorial talk is basically how the generation of true randomness is very crucial and very important for every QKD privacy protocol, and in particular for QKD. And also what I mentioned, that the very important parameter to estimate is this conditional mean entropy. Okay, that this is the parameter that you need to evaluate, and depending on the physical assumption that you are doing, well, you can exploit the entropy accumulation or the entropic equipartition theorem to get estimation, or other technique to get estimation on this parameter. And of course, it is very important to determine which is the specific framework that you are considering, trusted, semi-device, or full device independent. And as I showed also with the experimental data, you have seen clearly that going to trusted to full device independent, you go from high rate, let's say, more assumption, to very low assumption, but very low rate. Okay, so it really depends. It's a choice of trust and a choice of on your specific application, if you want to have, let's say, more device independent or more fully trusted QRNG. And so this really represents a kind of trade-off between practicality and security that you can, let's say, you should evaluate case by case in your specific case. So with this, basically, I'm end of this presentation. So thank you very much for your attention, and I, of course, any question is very welcome. Thank you.
Okay. Are there any questions? Oh, yeah, a lot actually. It's coming. One second.
Microphone, please.
Behind you.
Thank you. Thank you for the interesting talk. I want to ask about seed. Do I understand correctly that all these protocols require at least initial seed, and maybe rare, but it's refreshing? But how do we obtain initial seed? In quantum key distribution, there is the same problem with authentication. We also need to have initial key, but it's in principle theoretically clear how to do this, to send a tank, soldiers on a tank with flash card with a key. But here, if we don't have yet true random number generator, who will generate us the seed, and especially if we need to refresh at least sometimes?
Well, let me say, in my understanding, actually, this is actually the same problem. It's not a different problem, because even in QKD, when you send the initial seed, you need to generate the seed.
Yes,
okay?
Yes. So, I mean, in QKD, if we already have a random number generator but don't have an initial key, then we can send a flash card.
Yeah, but as I said, so the initial problem is to have initial seed of randomness. Okay, so of course at the beginning you need to trust something. Okay, so you need to start with a very small. Let's suppose that the seed that you need for device independence, for instance, can come from a trusted quantum random number generator. in that case, for a trusted random number generator, you don't need any, let's say, any initial seed, okay? Let's consider, for instance, vacuum fluctuation. You just do vacuum, homodyning, and then you get a random number. So the idea is that the initial seed should be trusted. You should use some trust at the beginning. Of course, this is only the first seed, because then you can recycle the randomness that you are generating from your protocol, right? So it's very similar also in QKD. You have only the initial seed of for authentication, and then you use the key that you're producing for the next authentication.
And for trusted generator, we don't need a seed. We can use a deterministic extractor, randomness extractor.
Well, in that case, you can even use a deterministic extractor because you know exactly what are the probability distribution. So in this case, yes, you can.
So the solution to use trusted with deterministic extractor. Okay, thank you.
Okay, you're welcome.
The one next, yeah.
So thanks for your very nice talk. So I want to ask about page 16.
Okay, let's
about
go.
The instructors.
Great.
So these 16. 16.
16, sorry.
No, it's okay.
Here.
So, okay. So it says that deterministic variable length instructor require no correlation of input, so it's like a fundamental result, or?
Is it, sorry?
So is this a fundamental restriction on instructors?
Well, for variable length, yes. If you have a variable length, you need something that is not, you need no correlation in your string, basically. You know?
Okay, yeah, because that would like cause some problem in variable length QKD, because then, I mean, if variable length QKD, then your input.
No, yeah. but in variable length QKD, what you should use is seeded extractor.
Okay, so you mean unseeded? Okay.
So with the seeded extractor,
okay.
then you can do very, very good stuff. Let's say there are no problems. Let's say, okay.
Yes.
So if you use a seeded extractor, this is what is typically used in QKD, right? In QKD, yes. You use something like this. You have some seed also for the the extractor, but then these have no problem, because this is what was shown, that this kind of extractor are secure against quantum side information. Okay, so this is what we have.
Yes, I see. So the last pages was about non-seeded instructors.
Constant instructor.
Oh, constant instructors. Okay, I see. Okay. And also, thanks, and also on these pages, there's like a typos here.
Okay.
No, the pros and cons are not. And the bottom line,
thank
the
you.
pros and cons
Yes.
are exchanged.
Thank you very much. Yes.
So, thank you for your talk.
Thank you.
Okay. There's one behind. Yeah.
Yeah, thank you for a great talk. My question concerns SDI based on vacuum fluctuations. Can you one more time explain the main feature of it, since we here in untrusted case as in trusted assume that all equipment is sealed, so everything inside of vacuum source is a trusted device with no access to if. So how can she hack it exactly, hack these sealed box? Because I know from engineering point of view, they are same like boxes. And the follow-up question here, the use cases for SDI, you show the commercial product as well for this type of QRNG. So is there medical sensitive information or maybe some other use case? Thank you. Okay,
so let me say, I have, if I correctly understood your question. So, well, the idea here is actually, to me, what really device independent means is not that you take the device from an eavesdropper, right? device independence actually means resistance against imperfection. So this is what you have to think about. So the idea of device independent is that you don't need to, let's say, to characterize your device, because it's the output that give you the information. For trusted, when you trust a device, it means that you need to characterize it, okay? So the entropy that you generate is only correct if the characterization is good, okay? So in this sense, the semi-device independence is a kind of trade-off. So it means that you need to characterize not the full system, but only part of your system, okay? And of course, this is increasing the security, no? Because let's say, for instance, what you have to do in trusted random number generator, so from time to time, you need to calibrate the system. Huh? So if you have a semi-device generator, you calibrate only part of the system, not the full system. Okay. So this is an example why, to me, this is relevant. But because, of course, no, there is always this example. If you have a device from, let's say, an adversary, well, you cannot trust it because you cannot know if there is some Wi-Fi signal that's going out with the data. So it's not really, let's say, it's not really related to an adversary, but it's related more to imperfection.
Mm-hmm. I get it. Thank you.
Okay, thank you.
Yeah, I have a question. Thank you very much for the, here.
On the back.
Okay. Yeah, thank you very much for your great overview. My question is, from the beginning you mentioned that for a typical QRNG, I mean the typical prototype is a single photon on a beam splitter, which means that you have to start with a sub-Poissonian state or a single photon state. But the examples, some of the examples you have shown, they start with laser diode or a laser or some kind of a non-classical light sources. I mean, mostly those are coherent light sources. So how do they call it a quantum random number generator?
Well, the example that I'm showing here was, for instance, no, if I correctly understood, sorry.
Yeah, for example, the ID counting systems, or I mean, most of the commercially available systems, they mostly start with laser diode or like.
Yes,
Yeah.
attenuated to the single photon system, yes. But let me show this in particular, no? Now, this random phase. This is a classical, completely classical state somehow, right? These are coherent states. However, you see the quantumness here because what you are doing in this gain switching is a kind of vacuum amplification. No? You can interpret this like you have the vacuum and then you amplify the vacuum with the cavity of the laser, and at the output, the phase is the phase of the vacuum that is completely random. Now, this is a way to interpret it. So basically, what you are doing with gain switching is basically, let's say, reading the phase of the vacuum and encoding into a classical system. This is the way I see it. Eh?
I got it for this kind of a system, but I mean, system with the photon arrivals. I mean, the simple types are laser diode, and then you have a beam splitter, and then you are detecting the reflection and the transmission. So in that case, it's just like a coherent light source. And then, but still they call it a quantum random number generator.
Yes, yeah, because of course, let's say, as I said, this is a trusted generator, okay? So what we are assuming is that we know the physics, we interpret this with the quantum physics. And what you can say in this case is that even if you have an attenuated coherent light, attenuated at the single photon level, you cannot predict which of the two detectors will click, okay? So from this point of view, is purely quantum. But I can understand that could be debatable, let's say, okay? So let's, I don't want to defend, let's say, to be, it's a very subtle and
but even if you write the state, you cannot get a single photon state with this kind of a photon sources, right? The coherent state.
Yeah.
But some people really call it a QRNG, and I mean, yeah.
I could agree with you, but Yeah, it's just an example, just to put it.
Yeah.
Another question from the front.
Yes, thank you. And thank you, Pino, for the great tutorial. Just a comment on that. Even a coherent state with a long coherence time is completely delocalized. So when you measure it in time, you can have a quantum effect, I think.
Yeah.
However,
thank you. Yeah, this is a good, good comment. Thank you.
My question was about, you stressed the importance of measurements in quantum random generator, but then the detector is a classical object with dark counts and inefficiencies, and sometimes you have the ADC, analog to digital converter, that has to match with the source to guarantee in a trusted random number generator the quality of your trusted numbers. So especially when you go to high speed, right? So how do you take this into account? This is like an art.
Well, this is, of course, this is a very, very relevant question. In order to deal with that, you need to have the more precise model of your, so it depends in which framework you're working. If you work into device independent, who cares? No, it's your data that tells you. If you work in a device dependent case, you need to have the most precise model of your system. So this is the simple answer. No, the better model you have of your system, the more secure is your evaluation of the entropy. Okay.
So even with the homodyne generator from vacuum, you still need an extractor to take into account of this potential.
Yes, absolutely, absolutely. Every imperfection should be taken into account. Yes.
Okay. Thank you.
Okay. So we're already inside the time of the coffee break. So let's thank once more the speaker.